So I'm really glad to be here, mostly to tell you that in the last few years, as you'll see, you've been slowly, silently sliding from the frying pan into the fire. And although Brian says you don't have much power, your responsibilities have gone up quite a bit, which is not great news. So what I'd like to do is run you through the earthquake story fairly briefly and then talk about some of the implications. And Brian gave me a laundry list of things to talk about here that would take me past midnight, but you'll have to get the hook and pull me off when my time's up. Okay, let's go. So for any of you who watch this show, you constantly see Sheldon ragging on geologists as being not a real science. It's just beer and guessing. And he's mostly right. But I'll try to make the case that we're starting to catch up a little bit. And if you're talking about a gigantic disaster, you might as well start with a joke. So there it is. And so the reason that geology is about roughly 100 years behind the other sciences is a long and sort of funny tale. But if you think, to put this in perspective, 50 years ago, this is the 50th anniversary of Apollo. My dad was one of the 400,000 engineers who worked on Apollo, the communications gear. And so 50 years ago, we were hopping around on the moon installing seismometers and other experiments on the moon. And at the time that happened, plate tectonics, which is the be-all and end-all of Earth science, was 6 years old. We only figured out how plates moved and where earthquakes came from in 1962, roughly, and it was over a pretty short span of time. And before that, all the explanations for mountain building and volcanoes, the Cascade Mountains and all that, were basically something like the stork brought it. I mean, it was just, they had some of the details right, but the whole story was just completely wrong. And here's Buzz Aldrin installing a seismometer on the moon, and there's the lunar module ascent stage hitting the moon and recording on the seismometer. So anyway, we knew more about the moon in 1969 than we knew really about the Earth. So the point of that is, why are we just learning about Cascadia? Why are we just learning about subduction zones? Why are we surprised when Northeast Japan has a magnitude 9 earthquake? It's because the science we're working within is only 50 years old. So we're making big mistakes and learning big things all the time. And that's why this is new. So here's Cascadia. Here's what it would look like. And sorry, this is kind of small, but this is what it would look like if you drain the water out of the ocean. Here, we're slightly off the map over here, but coast is here. The light blue is the shelf, and the deep blue is what we call the abyssal plain. This is the subducting Juan de Fuca and Gorda plates that are going underneath North America. And so in the early days of plate tectonics, I wish I could tell the story, but Cascadia played a role in launching the new theory of seafloor spreading and plate tectonics. And it was kind of interesting. There's a paper in 1961 that kind of helped launch the whole thing and make people realize that continents were moving around and new crust was being formed and old crust was being sucked under, essentially, is what a subduction zone is, in 1961. And then right after that, everybody just completely forgot about Cascadia. And the reason was it was missing one key ingredient that every other subduction zone in the world had. Anybody know what that was? Earthquakes. It was dead silent. All the other subduction zones in the world attracted the global seismologists and the big new plate tectonic theorists to go study them and explain them and test them to see if they fit the model or didn't fit the model. And Cascadia just sat there completely silent, so everybody ignored it for a couple of decades. But around the early 80s, people started to realize that this was the only silent subduction zone in the world, and so when you get to an anomaly like that, that starts to attract your attention. And people start going, well, wait a minute, how can that be? How can this be the only one of its kind? And so in 1964, we had a giant earthquake, a magnitude 9.2 in Alaska. In 1960, we had the world's biggest earthquake at 9.5 in Chile, and people started to look at this and go and wondered, well, what if this is kind of like those instead of just being dead and silent? And so an article was published in 1984 that had the Space Needle in Seattle, and the title photo and just saying, hey, what about Chile and Alaska? What about this thing? And people kind of went, uh-oh, what if they're right? But meanwhile, people tried to explain the silence of Cascadia in two ways. One way was they thought that maybe all the huge amount of sediment coming out the Columbia River, settling on the abyssal plain in deep water, maybe all that kilometers thick, very wet sediment was sort of lubricating the whole plate boundary, and it was just slip sliding away happily and silently. And nobody really published that because Chile and Alaska also have lots of sediment, so it didn't really make a lot of sense. And the other possibility, which nobody could really refute, was that maybe these spreading ridges, this is the Gorda Ridge and the Juan de Fuca Ridge up here, that were generating new crust, maybe they had just died. And there were places in the world where that had happened, and the resolution was less than 1 million years, so if it had died within 1 million years, that would be fine, that would work. And the whole system would freeze, looking anatomically correct but dead, and that would work. But nobody really published that either. And then in 1980, Mount St. Helens went off and reminded everybody that it wasn't dead, and that was a fairly graphic reminder. And in fact, Mount Shasta had gone off in 1912, and so it was never really taken very seriously. But then when that article came out in '84, if you remember the Alice's Restaurant song, he gets to a point in that story when he says, and there was a third possibility that nobody had counted upon. And the third possibility was that Cascadia was a completely locked fault and it just hadn't gone off in recorded history. And throwing that little possibility out there, the science community thought, no, probably not. But as it turns out, that turned out to be right. So in 1984, a Canadian geologist named John Adams found some deposits out here in deep water. He didn't find them, actually. They were collected by people at OSU in the 60s. What he found was the core logs from those things, and what he found was some deposits out there called turbidites. And turbidites are just submarine landslide deposits. They can be caused by earthquakes, floods, a whole variety of things, but he found some interesting stuff about them. That I'll talk about some more. And then in 1987, a guy named Brian Atwater, USGS guy, found some stratigraphy like this, well, actually this stratigraphy in Willapa Bay. And what you're looking at is on top of this thing is the modern marsh surface, and below it is some subtidal, below high tide level mud, and then there's some sand here, this light thing, and then some peat, and the peat is just an old marsh surface. And he started dating this stuff, and this stuff was about 300 years old, and the sand layer on top had marine fossils in it, so it wasn't a flood coming off the land down the river systems. And the other thing is this peat is degraded marsh plants, and they're the same plants as the ones on top. The problem is these marsh plants are really sensitive to tide, and they don't like to change their level more than about 10 centimeters. And here they are about 1 meter apart. So something happened here over a short period of time that put this marsh at a different level than that marsh by about 1 meter. And it happened pretty quick because this sand sheet on top of here, it basically buried the marsh plants in growth position. So they died by being smothered by sand that came from the sea. And as the story began to unfold, it turns out this sand sheet thins as you go upriver and then fades away. So it does the opposite of what a flood deposit would do. And then just to top it all off, these divots in it here are Native American fire pits. So something happened to change sea level relative to the land really quickly, took out a Native American village, buried the marsh, and then over several hundred years put intertidal or subtidal mud on top of the whole thing. And eventually a new marsh grew on top of it. And so Brian cast around for possibilities for this and finally decided that it wasn't the sea level that had changed over time, it was the land level that had changed really quickly, like in a matter of minutes, and put this marsh underwater by about 1 meter. And so we thought this was a completely outrageous, crazy hypothesis. Nobody had ever suggested such a thing. And I was a graduate student at the time. I went on this field trip, and I remember us all sitting eating our lunches at the state park benches and whatnot, going, nah, that's crazy. That couldn't be right. So, but Brian, he doggedly stuck to this hypothesis, and it pretty quickly became apparent that, and as he said in his talk, he would put his poster up, he would say, well, if you have a better idea, let me know. And there was crickets. There was no better idea. So in the years from, say, 1985 to about 1990, there was a paradigm change, and Cascadia went from a completely aseismic, silent, harmless subduction zone became the newest producer of very large earthquakes. And the icing on the cake, or the golden spike, as it were, is this. So this is a representation of a tsunami that was launched toward Japan. And so when Brian and some tree ring experts, David Yamaguchi and others, were working on this, they dated this event down to within a few decades of the year 1700, 1680 to 1720-ish. And then the tree ring guys got it down to the fall of 1699 or the spring of 1700. It's pretty good for geology. And then it turned out, though, that the Japanese had a record of a tsunami that arrived in the year 1700 without an earthquake. And so Japanese word for tsunami is a Japanese word. And so they're very familiar with this. They come in pairs. And the tsunami is going to come 20 minutes later, an hour later, whatever it is. But they always come together. And this tsunami arrived by surprise. It killed a few people, destroyed some boats, and did a lot of damage in coastal warehouses around Japan. And so through some careful sleuthing, Japanese colleagues figured out that this thing, figured out the water levels of this thing at all these coastal sites where the warehouse keepers would report how much rice they lost to the shogun to get paid back. So essentially an insurance claim. And maybe unlike today, I'm pretty sure they didn't exaggerate their insurance claims, because in the Shogun era, penalties were high. So I'm pretty sure they maybe underreported it, if anything. And an important thing to this is they had the date. So that's how we know the last Cascadia earthquake was January 26, 1700, about 9 p.m. And so, Kenji Satake modeled this tsunami from all the possible Pacific Rim sources and settled on Cascadia as the source, as the only one that could really explain the water heights and the wave heights in Japan. So suddenly we've gone from completely aseismic to we know the time of day of the last earthquake, which is pretty cool. And so here's Brian Atwater working in his preferred environment in the mud in Willapa Bay. And then there's more evidence. So we've all driven by the coast and seen scenes like this with snag trees just standing there and don't really think much of it. But a lot of these trees were actually killed by the last earthquake, and they're 300 years old. And you wouldn't necessarily think that just looking at them. And so if you saw one of these things down in radiocarbon date, the last outer ring, they often turn out to be 1700. So these things, like the earlier slide, they were dropped into the bay, killed by salt water, and because they're western red cedar, which we all know works great for decks because it lasts a long time, resists rot, they're still there. And so this is the general scene. So in a subduction zone, the oceanic plate is the weaker of the two plates, and we're used to thinking of continents and things like this as being very rigid things, but in the global sense, they're kind of rubbery and soft. And so the oceanic plate that's going under is relatively stronger than the continent of North America. And so the continent, when the plates are locked, bulges up. And then when the earthquake happens, that bulge lets go, and the coast goes down, and the outer part goes up, and that shift is what causes the tsunami. And so locally, you have your forest growing down to its saltwater limit. It suddenly drops into the bay. A little bit later, the tsunami comes in and lays down a sand sheet, and then days to weeks later, the trees die. And then the space starts to fill up with bay mud, And then over time in the seismic cycle, it starts to come back up again. So you wind up with those snag trees sticking up through the present surface and still they're lasting for a few hundred years. So the evidence for great earthquakes was there all along, and just nobody knew what it was or what we were looking at. So here's a cross section of through the middle of Oregon. Here's North America in gray. This is the topographic bathymetry data in blue. Here's the Juan de Fuca plate. Down here, subducting obliquely, and so a lot of things happen during these giant earthquakes. Not only does the land go down, the land is shaking for 3 or 4 or 5 minutes maybe. So it generates landslides that affect the offshore region, submarine landslides, landslides within lakes, landslides that create lakes on land, and so forth. And I'll show you a little bit of what I do. So I study these turbidites, the very same ones that John Adams found in 1984. And so this is Cascadia turned on its side. And let's see if I can make this go. And so if you shook the whole thing and you had turbidity currents coming down the channel systems, this is what it might look like. That's maybe 24 hours of run. And so these things are very well known. They were mapped by OSU and UW students back in the 60s. And so the system and how it works was very well known. What wasn't known was that these deposits that are out there might be indicators of earthquakes. And so here's what a core sample looks like. This is just 4-inch sprinkler pipe. This is a couple of thousand years of record, and these bands are the turbidites. And what it says here, if you can't read it, is turbidites are easy to capture, but what do they mean? Well, they're easy if you have a 300-foot ship and a piston coring rig and things like that, but relatively easy. This is just a giant lawn dart, and you just let it fall into the bottom and just bring it back up, saw it in half, and this is what you get. And so what John Adams realized, that even though people in the 60s had worked this out pretty well, they'd never talked about earthquakes, because remember, plate tectonics in the late 60s was only a few years old, and the science of paleoseismology, studying old earthquakes, didn't exist in 1969. There was no such thing. And so they didn't talk about earthquakes. They just dutifully studied the sedimentology of these deposits and where they came from and so forth. And what Adams proposed was something pretty cool. What he noticed was, first of all, that you all know about Crater Lake, which was Mount Mazama. It went off 7,600 years ago and blew ash all over the Pacific Northwest and as far as Greenland. It's in the ice cores in Greenland. And so it's very well known, very well dated. And so what Adams found was each of these cores had the Mazama ash in them, and that was well known also. But what he noticed was that if you counted from the top, you would always find the ash at the same level in these cores. 13 turbidites down, you just count from the top, and he found the ash at the same level in the 13th turbidite, here, 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 and here. And so he thought, well, what are the chances if these landslide deposits are caused by earthquakes, floods, storms, all sorts of things, what are the chances that you'd find this ash at the same level everywhere? That seems pretty unlikely. So he proposed these were generated by earthquakes, which would generate synchronous landslides everywhere and would explain the data perfectly. And then he went one step further. He found that there's a confluence right here between two major channel systems, and both arms of the confluence, that ash was at the 13th turbidite. And then when you go downstream, it's also in the 13th turbidite. So there's only two possibilities. Either you lost 13 going downstream from the confluence, or they all arrived at the confluence at the same time and merged, and you get the same number everywhere. And merging at the same time from two different sources means synchronous, and synchronous means earthquakes. And so he was able to make the argument that the last 13 turbidites throughout the region were great earthquakes triggered by Cascadia. And sounds a little outrageous, and everybody sort of dismissed it at first, but it turned out to be right. And so we wrote a proposal to NSF to go out and prove John Adams wrong because we didn't believe it. And so John Adams is a land geologist. He did his work at his desk. We went to sea with a whole bunch of instruments and stuff, and we did it the hard way. And we collected cores and took CT scans. And we correlated cores with basically oil industry methods. I'm going through this kind of quick. This is where the 4 3/4 gallons goes. But, yes, there is going to be a test, so I hope you're taking notes. But the bottom line is basically we adopted oil industry techniques to correlate these turbidites from place to place because the oil industry does the very same thing in the Gulf Coast and the North Slope and all over the place because their reservoir rocks are the very same things, turbidites. And so it's quite easy to adopt their methods, only we had the cores, which they don't normally have. And we were able to radiocarbon date each one of these things and correlate them using age and the physical properties. And the bottom line is they correlate just the way Adams said they should. And so we were wrong, he was right. And then a Canadian group recently went out, and I'll just go over this pretty quickly, and replicated what we did off Vancouver Island, with a little bit north of where we were able to go. And basically correlated their turbidites and linked them to ours to finish off the story, to get to the northernmost end of Cascadia. And they were successful in that as well. So this is our typical field vehicle. This is the Tommy Thompson UW's 270-foot ship. This is what we normally do, and it takes about a month and about $2 million or so to go out and test this hypothesis. That's just to get the data. But it turns out that you can just as well take a couple of Grumman plastic canoes and a sheet of plywood and go out to almost any lake, which I wish I'd known that earlier, and collect hand-push cores, and you also have essentially the same record, a very nice record of Cascadia. These things are complicated a little bit by the fact that the watershed they're in may have other inputs, storms and other things that you have to sort out. But it's basically doable, and so we've been working in some lakes in Oregon and Washington to put together that story. And I won't say too much about it, other than to say that we now have a land record of Cascadia earthquakes, we have a marine record of Cascadia earthquakes that mesh quite well, and now we have kind of a growing lake record of things. So we have a stool with 3 actual legs that doesn't wobble very much, and all of these lines of evidence are singing the same tune. And so the bottom line is that Cascadia has gone from kind of 0 to hero in a pretty short time, and it's now kind of arguably, I would say, the best known subduction zone in the world. We have a 10,000-year earthquake record recorded in lakes, offshore, and at the coast. All the records are quite well aligned. And this is all now built into the USGS National Seismic Hazard Maps and building codes and so on. So that's kind of the short version of it. And the summary slide is a video. So this is Cascadia, the movie. And it doesn't have the rock cast in it yet, unfortunately. But this is Cascadia. So it's a series of slides. So this is 46 earthquakes, 10,000 years of history, and playing at about 200 years a second. So you're going to see some red blobs going off, and the red blobs are what we think is the earthquake patches, and you're going to see some dots on the map, and the dots are where the data is for each event. So we're starting at 10,000 years ago and going forward in time. And so right away you'll see that there are differences. There are some that go the full length, and there are others that don't, like these. And sometimes there are big gaps in these that are filled by a series of small events. So we're down to about 4,000 years. And as we get down below 4,000 years, you'll see a lot more dots appearing on the coast because the land record kicks in at about 3,500 or so. So now we're down to 2,500 years ago, and you'll see a yellow thing down here. That's this northern San Andreas fault. which not coincidentally is going off at about the same time in some events. That's another grade B movie story that we don't have time for. So now we're down to 480 years ago, the penultimate event. And then the well-known AD 1700 earthquake. And what you might have noticed right away is that the 1700 earthquake, magnitude 9 as calculated from the Japanese tsunami, is not a great big huge standout bigger than all the rest. It's actually average. It's typical. And so, and there it is. So the Hokusai print here showing the wave arriving in Japan, that's not really the 1700 earthquake. And then this, many of you probably know this story. The Native Americans, when the geologists had eventually figured this out in the 1990s, and still continuing, the Native Americans essentially said, why didn't you just ask us? We knew about that. And they did, but they knew it as the Battle of Thunderbird and Whale, two of their big gods. And the battle involved a lot of heavy shaking of the ground, washing away of villages, and things like that. And that's how they told the tale. And it had a land use planning parable at the end of it. They said, oh, by the way, in case this ever happens again, don't build your villages too close to the coast. And so it is around the world in subduction zones. Many of the indigenous cultures, they know what to do in a tsunami. They don't have to relearn this lesson as we are. They already know what to do. And so did the Native Americans. And so here's just the summary of that. But basically the idea is you have about half of the events are full-length events, magnitude 9-ish events, and then you have a series of smaller events at various places, mostly in the south. So the probabilities are spatial. They're not the same in Seattle as they are in Coos Bay. And so the one nasty math plot I'm going to show is this one. So everybody wants to know what's the probability. And you've probably heard different numbers. So how many of you have heard different and conflicting sounding numbers for probabilities? Okay, almost everybody. So the reason for that is they don't actually conflict. They're just different for different places. So you saw the movie, and you saw the big ones only, the north end only sees the big ones, and the middle sees some of the smaller ones, and the south part sees all of the smaller ones, essentially. And so what that means is, if you're in Seattle or in the Washington coast, you have a recurrence time of about 400 to 500 years. And so this plot is a log-log plot, probability over here and time this way. And just suffice to say that if we look out 50 years in the future where this dot is, and this is the past and this is the future, most of the recurrence times between events are in the future. So we haven't got to the average repeat time. It's been 318 years of a 400 to 500 year cycle, so we haven't even got to the average time yet. So probability there for Seattle is about 10 to 15% in 15 years, which sounds low, but it's actually pretty big. It's about the same percentage as Japan had when Tohoku went off. On the other hand, if you look at the same plot for southern Cascadia, here's the target date here, here's the future, and here's the past. Well, we've blown through 75% of all the known intervals between earthquakes for southern Cascadia. There's only 6 that we haven't exceeded. So we're 319 years into an average 240-year cycle. So we've sort of sawn 3/4 of the way through the branch, and it's cracking, and we're sitting on the outboard side of it. So, and just to make things really screwy, these things, now that we have a very, very good detailed earthquake record, they don't come evenly in time. They don't come evenly spaced at all. They're spread, they're clumped. And so this is 2 different versions of clustering plot that just shows that here's time 0, you are here, and then 10,000 years back is here. And so for the last 1,500 years, we've had a cluster of 5 earthquakes averaging 320 years apart, exactly the average that we're sitting at. But then before that, we had a 1,000-year gap. and then there was another cluster of 5, and then another 1,000-year gap. So this is what makes probability people just walk out of the room and go, well, I don't even want to see that plot because I can't do anything with it. And so this is kind of an interesting thing that we know, but we can't figure into the probabilities because we have no idea if it's going to repeat or if it means anything. If it's just random coin flipping, which it could be, then there's really nothing we can do about it. And so, so it concludes the talent portion of our program. If you can't read it, it says, it was only a minor earthquake, but the Etch-a-Sketch gallery was ruined. So I kind of blasted through the geology really quick so we'd have more time to talk about other things. And so in Japan, I was there during the Tohoku 2011 earthquake. I was back about the same distance as, say, Corvallis or Portland was, and so the shaking there was impressive, but actually made me have some confidence that these things are manageable. You know, it didn't knock us to the ground, it didn't knock the building down, it didn't actually damage buildings in Japan at all because Japan's very resilient. On the other hand, at the coast, everybody's seen all the movies, and I'm not going to belabor this too much, but it was just incredible devastation. And the thing is that in a subduction zone earthquake, things are not going to turn out well. That's a given. And in Japan, even though they lost 18 to 20,000 people, this was a success. This is the biggest success in subduction zone earthquakes that we know of. In Sumatra, with a similar-sized earthquake, they lost 250,000 people around the Indian Ocean. And Japan did 10 times better than that, performance-wise, because of education and resilience. And that's the difference. So, unfortunately, you have to look at this picture and say, this is what success looks like.
Chris, what about aftershocks?
Aftershocks, there are lots of them, and they scare the crap out of everybody. But they typically don't do very much. They're not going to do much more damage, and they're not going to generate more tsunamis. At least, you know, from where on the learning curve we are right now. But that's a good question. So here we are, meanwhile, back in Pacific Northwest. So we've built all of our fragile infrastructure, not knowing anything about this stuff. Nobody did anything wrong. We just didn't know it. And so we have turn-of-the-century cities, not the last turn of the century, the one before that, sitting on a magnitude 9 time bomb, essentially. And so we have, you know, just for a few examples, we have 300 bridges that look like this, some of which, to me, don't look like they'd stand up to much of a breeze, let alone an earthquake. And ODOT is well aware. We have 1,000 of these unreinforced masonry schools that are getting retrofitted 3 or 4 a year. At that rate, we have a long way to go. And then we have unreinforced masonry buildings by the thousands. Portland has 1,600 of them. Seattle has a similar number. And every town, you guys all know this far better than I do, every town is full of these things. And this is what an unreinforced masonry building looks like. It's totaled in a magnitude 4 earthquake. So we have a significant problem. And so on the laundry list of things that Brian asked me to talk about that I'm not going to get to talk about all of them, there's no top-down directive about what to do about this huge building stock of unreinforced masonry buildings. It happens town by town. And you guys are the mayors of all of these towns. Seattle and Portland recently have attempted the first baby steps in doing this. Seattle's been going around this cycle for almost 2 decades now. Portland, 3 or 4 years ago, tried to start an initiative to just brace the parapets in Portland. This is just putting some steel rods out there to keep the parapets from falling off the buildings. It's cheap and simple. And I went to give testimony there, and there was something like 300 building owners to protest the poverty it would cause if they had to put braced parapets on their buildings. So they backed off to just placarding the buildings, saying it might be an earthquake hazard, and they got even more building owners showing up, including the NAACP and complaining about gentrification and all sorts of things. And it was just an amazing pushback.
Because we are at time.
Okay, okay, I got a long way to go. I'll go fast. So, so around the world, I just want to emphasize that land use planning is the way this is being done in Japan and everywhere else in the world. I'm going to lean toward tsunami now for a minute. And so in Japan, they passed a national law in 2012 after they were badly surprised by that earthquake. And basically, the tsunami inundation zone is considered uninhabitable. And the way they deal with it is they zone the area and they define what things can take place. And in the lowest zone, the red zone, 2 meters of inundation or more, you're not allowed, housing is not allowed there at all. Factories are not allowed, or there are things like fish plants are allowed there, but no night shifts, and they have to have a well-defined evacuation plan. So they're very strict about this stuff. Although they let the municipalities figure out the details of how they're going to implement it, this is now national law in Japan. Okay, so I'm going to skip quickly because I'm already out of time. This is one of the most extreme examples. So in Ishinomaki, or Minami Sanriku, this is how the town was before the tsunami. The town was all at the low level, hillside here. They've now reshaped the hillside and put the town mostly up here, leaving behind only fish plants and port facilities and things that obviously have to be on the water. So the mayor of Minami Sanriku, who you'll meet in just one second, just said, no more. We're not going to get hammered anymore. And so Oregon is using the same approach. So this is where the sliding from the frying pan into the fire takes place. So at the state level, there's not a ton of leadership going on. You guys are probably feeling like you're kind of hanging out there by yourselves, and you are. And so towns and municipalities and counties are now working with DLCD and NOAA on land use planning, sensible land use planning for towns in tsunami zones. And you guys probably all know this far better than I do. And here are the participants so far, list of counties and towns. It's growing all the time. They don't have funding to support it as they did a few years ago, but it's still moving forward. And here's just a few slides from their programs. And so this is based on the 2013 Dogami Tsunami Maps that have been widely available, but not adopted as official policy by the state under some pressure. And so this is just a summary of the mapping and modeling. Oregon, it turns out, has a tsunami modeling program that's kind of the envy of the world in a way. Canada and the other states surrounding us wish they had this, and they don't. So Dogami, even though they've caught a lot of flack lately for budget problems, has done a tremendous job in what they've done. And we're actually ahead of Japan, we're ahead of most countries in the world, and the Canadians wish they had this. Anyway, so this is the program, the DLCD NOAA program. I'm going to flip through these fairly quickly. Evacuation planning routes, Tsunami Ready, resilience is well underway. And so this is city by city now. And then something funny happened. This summer, Oregon, the legislature rescinded Senate Bill 379, the official tsunami line that we had, in what I would call, I'm just going to be blunt about it, a major step backwards, leaving essentially nothing in terms of, so SB 379 prevented building schools and critical facilities in the tsunami zone. So we've now taken that away. I'm not seeing a rush of people to build schools in tsunami zones, except for OSU maybe. So maybe nothing will come of it, but at the moment, there's no restriction on the Oregon coast from building really anything. You can do anything you want. And the idea was that would be replaced by a building code provision provided by the ASCE engineers. Well, there's a problem with that. So the ASCE stepped out of what they normally do, which is building strength calculations, structural calculations, and did some tsunami modeling. And in the interest of time, the tsunami modeling didn't work out very well. It's never been published. It's not vetted at all. and the results are fairly haphazard. It's not a world-class effort. Essentially, it undershot what Oregon had already done by a wide margin. And these slides, I'll make all these slides available to you. The details of what went wrong are in there. But so now the Building Codes Division in the state of Oregon is faced with either adopting or not adopting this stuff. And if they do, we've essentially replaced what Dogami has done with a very underwhelming tsunami model that's going to confuse a lot of people. So in terms of what to do, my suggestion is follow the NOAA and the DLCD plan and have your own locally customized land use plan that uses the Dogami models, which would be essentially what a lot of towns are already doing. So I'm going to just skip over all these text slides about that and just finish with this. This is the public safety building in Minami-Sanriku, after the tsunami, obviously. So when you build a building to the new proposed building codes, it'll survive the tsunami. You'll have a steel skeleton standing there in a building that's going to be scrapped. You can't really use it again. And it has nothing to do with whether people survived or not. It just means that the building structurally will still be there. So this is the public safety building in Minami-Sanriku. This is Mayor Jin Sato, who we met a couple of years ago. He grew up in this town and became the mayor. And he was in this building when the tsunami hit it. And this is his picture from the cell tower. The building was too short, obviously, as the entire town went underwater. And he took this picture. 48 people died at their radio broadcasting stations trying to get the word out. And 6 of them survived by climbing up the cell tower. And so this is what a well-engineered building looks like in a tsunami. It's underwater and destroyed, and everybody in it perished. But the steel skeleton survived. So I'll just end on that cheery note and see if you guys have some questions. Yes, sir.